So in this lesson, I'm going to be discussing and explaining how to calculate the average atomic mass and percent abundance. So really quickly, remember your average atomic mass is different from your mass number. Your average atomic mass is actually the weighted average, and I'll explain what that means in a second, of all the mass numbers of an atom's isotopes. That's a long sentence, so let me explain it. And the way I'm going to explain this is actually with the very first example. Okay, so copper has naturally occurring isotopes with mass numbers of 63 and 65. So remember, since copper has an atomic number of 29, it has 29 protons, what that means is that copper 63 has 34 protons, while copper 65 has 36 protons. Remember, because mass number is simply protons plus neutrons. So it has two different isotopes, mass number 63, mass number 65. The relative abundance of copper 63 is 71.2%, while that of copper 65 is 28.8%. Calculate the average atomic mass. So normally, what we've done to average in the past is if I said, hey, go ahead and average 63 and 65, what you would have done is taken 63, added 65 to that, and divided by 2, and called it an average. And then you could say, oh, there's my average atomic mass. But we can't do that. And the reason why is because by adding them together and dividing by 2, we're assuming that their percent abundances are the same, that they're both 50%. They contribute the same amount, but they don't clearly. Copper 63 contributes 71.2% of all atoms on the Earth, while copper 65 contributes 28.8% of all atoms. So what we need to do is a weighted average. And this is how a lot of grades for classes is determined, assuming that every category for a specific class, like homework, tests, quizzes, etc., are not all worth the same percentage. Here's what we do. We're going to take our percent and we're going to convert it into a decimal. So I've got 71.2% here, and I've got 28.8% here. Okay, and I'm going to convert both of those into decimals by moving the decimal place over 2 places, 1, 2, because remember, percent means per 100, so I need to divide by 100. So this becomes 0.712, this becomes 0.288. Okay, and what I'm going to do is I'm going to multiply both of the mass numbers by their relative percent abundance, add them together, and that will be my average atomic mass. So instead of getting confused by wording, let's just do it. So 63 is the mass number. I'm going to multiply by its percent abundance as a decimal. And I'm going to add to that the other mass number, 65, times its percent abundance. Okay, and I'm going to get my answer. Now, once I get my answer, note that I asked you to round to 2 decimal places. So the answer I get, rounded correctly, will be 63.58. Now, the question becomes units. Mass numbers are simply protons plus neutrons. So the unit for this average atomic mass is not going to be grams, because remember, protons and neutrons are extremely small. So it wouldn't be 63.58 grams. Instead, there is a relative unit that was actually determined by studying carbon that we can use so that we get nice large numbers, even though we're talking about very small subatomic particles like protons and neutrons. And that unit is AMU. Okay, so all of the average atomic masses that you see on the periodic table, their units are AMU, average mass unit. I've rounded to 2 decimal places, so that's my answer. Okay, let's look at the next problem. There are 2 naturally occurring isotopes of thallium, thallium-203 and thallium-205. Use the average atomic mass of thallium listed on the periodic table to determine the percent abundance of each isotope. So now I'm changing the problem. Now I'm saying you can look at the periodic table and see that the average atomic mass of thallium is 204.38. So I'm not asking for you to solve that, okay? Which, by the way, for example 1, the average atomic mass of copper is pretty dang close to 63.58. It's actually 63.55. So that's a nice way to be able to check yourself when doing these problems. But for this one, not so lucky. So what exactly is it asking me to do? It's asking me to determine the percent abundance. So I don't know the percent abundance of either of these. But what I can say is, all right, if the percent abundance of thallium-203 is X, what would the percent abundance of thallium-205 be? Well, remember, since these are my two only isotopes, their percent abundances have to add up to 100. Okay? However, because I use a decimal rather than a percent in determining the percent abundance, and instead of saying they should add up to 100, they actually add up to 1. Okay? So X, which is the percent abundance as a decimal of thallium-203 plus something, has to equal 1. Okay? Well, how do I solve for that question mark? Well, if I moved X over, that would give me my answer. So the percent abundance of thallium-205 is going to be 1 minus X, because notice when you add X plus 1 minus X, you get 1. So now I'm just going to plug in these values to my formula. So 203 is the mass number, its percent abundance is X, plus the next mass number, which is 205, times its percent abundance, 1 minus X, equals the average atomic mass, which is 204.38. Okay, that's it. Now let's solve for X. So a little bit of algebra. We can do it. 203X plus 205 minus 205X, because I distribute the 205 with the 1 and the minus X, equals 204.38. Okay, now I'm going to combine like terms. 203 and minus 205, when I add them together, because this is plus and negative, 203 plus negative 205 gives me negative 2x. Okay. And then I'm going to subtract 205 from both sides. Lots of math, but that's okay, we can do it. So what that gives me is negative 2x equals negative 0.62. Divide both sides by negative 2. So what I get for my x, which I'll write up here, is 0.31. Okay, so the percent abundance for thallium-203, and notice it asked me to round to 2 sig figs, so I already have 2 sig figs. This is a decimal, I want to know the percent, so I'm going to move my decimal place back 2 places, 1, 2. So this is 31%. Okay. Remember, the percent abundances have to add up to 100, so if this is 31% for thallium-203, then thallium-205 would be 69%. So here's a really nice way, if you want to check yourself. I'm done, but if I want to check myself, what I can do is just the traditional average atomic mass problem now. 203 times its percent abundance, 31%, but I've got to make it a decimal, so I'm going to move the decimal place 1, 2 places, so 0.31. Add to that 205 times its percent abundance, which is 69%, and make sure when I do that that I actually get the average atomic mass of thallium, which is 204.38. And I do, so I'm all good. So these are my answers, 31% and 69%. Let's look at the next problem. All right, strontium consists of 4 isotopes with masses 84, 86, 87, and 88. Calculate the atomic mass of strontium. So this is more like the traditional problem we saw for the first one. The only challenging thing here is the percents. So notice for 0.5%, okay, to convert that into a decimal, I need to move the decimal place 1, 2 places. So that's going to become 0.0050. Okay, for 9.9%, I'm going to just write these out really quickly. There's 9%, there's 7%, and there is 82.6%. Okay, so I'm going to move my decimal for each of these. 1, 2, 1, 2, and 1, 2. All right, so now I can actually plug and chug. So I've got 84 for my first mass number for my first isotope. Its percent abundance is 0.005 plus 86, next isotope's mass number, times its percent abundance. Okay. Plus the next one, 87, times its percent abundance, 0.070, plus the next one, 88 mass number, times its percent abundance, 0.26. Okay, I'm going to plug in to my calculator, multiply each mass number by its percent abundance, add them together, and what I get is 87.71, okay, because I want 2 decimal places. My units are AMU. Quickly, you can check the periodic table. Strontium, if you look, has an average atomic mass of 87.62, so accounting for rounding errors, I'm off by 0.09. I'm okay with that.